Hello, today we're discussing carboxylic acids, the functional group that has attached to an alkyl group a C double bond O OH. That's a carboxylic acid. As we'll see in our upcoming chapters, the carboxylic acids are starting materials for what we call acyl derivatives. We got acid chlorides, esters, amides, thioesters. All of those can come from carboxylic acids. So carboxylic acids are very important synthetically, very important biologically. Many biological systems have oxidation pathways that end up at carboxylic acids. The carboxylic acid oxidation state is the most oxidized carbon can be, at least if it's in an organic molecule. If we oxidize a two-carbon chain all the way, we get acetic acid, right? CH3C double bond O, OH. Vinegar is a 5% solution of acetic acid in water. Butanoic acid is a 4-carbon carboxylic acid. OH, 1, 2, 3, 4. That's the smell of rancid butter or rotten milk, right? Butanoic acid, its old common name was butyric acid, which came from the same root as butter. That's what gave IUPAC the BUT prefix for a 4-carbon chain. What these carboxylic acids have in common is a strong smell, right? Acetic acid, it smells like vinegar. It's not a tremendously unpleasant smell. It's just sort of a sour smell. But the other carboxylic acids have very unpleasant smells, obviously, with butanoic acid. Other ones, the 3-carbon propanoic acid smells distinctly like dirty sweat socks or gym shoes or something like that, because the bacteria that are present when you're sweating actually produce carboxylic acids as a result. So somebody with BO, you're smelling the carboxylic acids produced by those bacteria, actually. Another group of carboxylic acids that are important are fatty acids, generally considered longer chain carboxylic acids. And the normal ones that we consider are 10 carbons and up. So usually just a straight chain. It can be saturated or unsaturated. They are precursors biologically to fats and oils. So animal fats can be in the form of triglycerides or phospholipids, for instance. You've probably learned a bit about those in a biology class, or you will in the future. Just for your information, you don't need to memorize any of these, but I'm just giving you some common names here of some fatty acids, names that you may recognize in certain places. So lauric acid is 12, palmitic 16, stearic 18. All of those are just saturated 12, 16, 18 carbon carboxylic acids. We'll learn when we're talking about esters later on how some of these can be used as surfactants and things like that. You'll see derivatives of these types of names on ingredient lists for shampoos and lotions and things like that. Unsaturated fatty acids, the naturally occurring ones, have cis double bonds. So where stearic acid was 18 carbons saturated, oleic acid is an 18-carbon chain with a cis double bond starting at carbon 9. Linoleic acid has 2 double bonds. Both are cis, 9 and 12. Alpha-linolenic acid has 3, all right, cis 9, 12, and 15. This last bit that I've shown you here, it looks like a little W, but it's a lowercase omega. What I've shown you here are omega-6 and omega-3 fatty acids. The omega is counting carbons from the end, right? Omega is the last letter of the Greek alphabet. So if it's omega-6, if I have an 18-carbon chain with a double bond starting on 12, that's 6 back from the end. Alpha-linolenic acid has it's 18 long, but has a double bond starting at 15, so that's 3 back from the end, counting backwards that way. So you hear nutritionally all the time about omega-6 and omega-3 fatty acids as part of a healthy diet. Trans fatty acids, we hear about trans fats and trans fatty acids. They're not naturally occurring. They're usually side products of catalytic hydrogenation of unsaturated fatty acids. So if you take some sort of unsaturated fatty acid like oleic acid or linoleic, things that come from animal fats and so on, and we do a reaction that we've seen before, right here, either one of these, right? If we do hydrogen with palladium, it'll convert that cis double bond into a single bond, right, creating a saturated fatty acid. But in the process, the double bond geometry gets scrambled and some trans fatty acids are produced, and those have pretty serious health effects with raising your cholesterol level, actually, and putting you at risk for heart disease and other things. So that's just some stuff for your information. Almost all of you will probably run into things like these in your studies later on. Naming carboxylic acids, the suffix for IUPAC nomenclature is oic acid if it's a carboxylic acid. So propane becomes propanoic acid. If we've got a chain of carbons, the C for the carboxylic acid is number 1, just like in aldehydes. So here we have 4-methyl pentanoic acid. A dicarboxylic acid, if it's just a simple chain like this, we've got carboxyl groups at either end of the chain. We'll just number from whichever end is closer to a branch, and if there's a tie like this, we use the alphabet to tell us which one has our numerical priority. So that's why this is 3-ethyl 6-methyl octane dioic acid. Notice we now have the E here, where we deleted the E's. In propanoic acid, for instance, here we have octane dioic acid because we don't have a double vowel possibility that way. If we add a little unsaturation here, let's just do something simple like this. A 1, 2, 3, 4, 5 carbon chain, methyl group on 4, but a double bond between 3 and 4. So that's going to be, let's number these, 1, 2, 3, 4, 5. It's going to be 4-methyl, 3-pentene oic acid. So if we have a carboxyl group, if we have C double bond OOH that's attached to a ring, we use carboxylic acid as a suffix. And then the place where the carbonyl, or where this carboxyl group is attached, takes numeric priority in the ring. So if I have a carboxyl group and a hydroxy group on carbons 1 and 4 of this cyclohexane ring, it's trans stereochemistry around rings. Remember, 1 up, 1 down is trans. So trans 4-hydroxy cyclohexane carboxylic acid. We've got a double bond here in the ring, but still the carboxylic acid is the primary functional group of the molecule, so it has numeric priority when numbering around the ring. This is 1-cyclopentene, right? Ene carboxylic acid. So only when we have CO2H attached to some sort of ring do we use that carboxylic acid nomenclature. We can use carboxy as a prefix, but so far we haven't seen any functional groups that have priority over carboxylic acids. So these have priority over all of the other functional groups that we've talked about so far. So definitely over any unsaturation, over any other carbonyls that we've talked about, like aldehydes and ketones, and as you can see in this example, it has priority over the alcohols and so on. So that's sort of a general rule. The higher the oxidation state, the greater the priority in nomenclature. It turns out because they have such distinctive properties and they're found so readily in natural systems like fruits ferment and so on, they were among the first organic compounds that were isolated and purified. Several of them can be purified by distillation or recrystallization, so things that have been, or really even just by concentrating a mixture that has been formed. So since they've been around, acetic acid, for instance, has been around since biblical times for 2,000 years or so on. So carboxylic acids do have more common names than other types of compounds. The ones that I want you to be aware of are formic acid and acetic acid. Formic. The root for formic comes from ants. It's a formic acid is produced by a certain type of ant, I believe. That was one of the first places it was isolated. Acetic acid comes from the root for sour. Right, that's where these names come from. Right, acetic acid, of course, being present in vinegar. So long before they had any idea what these were even made of, these words were used to describe their properties, essentially. So these ones that I want you to have are formic and acetic, as well as benzoic. We've seen that one before. Benzene ring with a carboxyl group on it. Formic acid is the one carbon carboxylic acid. It would, if we were doing strict IUPAC rules, it would be methanoic acid, and acetic would be ethanoic acid, but those two are so rarely used that formic and acetic are essentially used instead of them. So these ones that I've starred, formic, acetic, benzoic, are the ones that you should memorize. All these other ones, use this as a reference when you come upon a name of a carboxylic acid that doesn't make sense in an IUPAC way. You can take a look at these. So, we got oxalic, malonic, acrylic acid, maleic acid. A couple of interesting ones to show you here is lactic acid. 1, 2, 3. So it's a propanoic acid. It's 2-hydroxy. If we did IUPAC, that would be 2-hydroxy propanoic acid. Several of these are very important in biological systems, like maleic acid and fumaric acid, glycolic acid, lactic acid, pyruvic acid, malic acid, the metabolism pathway, the Krebs cycle, things like that you'll learn about in biochemistry. Make extensive use of lots of carboxylic acids like these. One other one that's not drawn on here that I ought to show you is citric acid. Citric acid has a 5-carbon chain with carboxyl groups on either end of it. So there's HO2C, CH2, C, CH2, CO2H. Okay, so it's essentially it would be pentane dioic acid. The third carbon has a hydroxyl group and has an additional carboxyl group. So it is a tricarboxylic acid with carboxyl groups on the end, as well as one attached separately off of the third carbon and a hydroxyl group. So that's citric acid, what gives lemons and limes and grapefruits their sour flavors.